This is Dr. Mohan Lakshmi, Professor and Head Department of ECE from Rohini College of Engineering and Technology. In this video, we'll see about the topologies of feedback amplifier. So there are four basic amplifier types. Each of this is being approximated by the characteristics of an ideal controlled source. The four feedback topologies are as follows: series shunt, series, shunt series, shunt feedback. So this can also be alternatively said as voltage series or series shunt feedback, current series or series feedback, current shunt or shunt series feedback, voltage shunt or shunt feedback. So voltage amplifiers with voltage series feedback. So you can see in the circuit diagram, so in the diagram which is given here, the input voltage Vi of the basic amplifier, it is the algebraic sum of the input signal Vs and the feedback signal V0, where V0 is the output voltage. So you can see here a voltage amplifier is there. There is a feedback network where the beta value is given by Vi by V0. So once it comes to the second type, which is current series or series feedback, so it is a transconductance feedback amplifier which provides an output current I0 which is proportional to the input voltage Vs. So the feedback signal is a voltage Vf which is added to Vs at the input of the basic amplifier. So this is actually, you can see here, this is termed as transconductance amplifier, and the feedback network beta is given by Vi by I0. And the third one is current amplifiers with the current shunt feedback. So this supplies an output current I0 which is proportional to the input current II. So this makes it as a current amplifier. So this has been denoted here as current amplifier, and you have the feedback network II by I0. So the signal, feedback signal is a current. If the input current of the basic amplifier is II, so you can give which is equal to Is plus If, and the output current will be I0 which will be equal to the load current IL. So the last one is voltage shunt or shunt feedback. The voltage shunt or shunt feedback amplifier provides an output voltage V0 which is in proportion to the input current Is. So the input current which is designated as II of the basic amplifier is the algebraic sum of the Is, that is source current, and the feedback current If. So you can see here, this is trans resistance amplifier, and the feedback network has a beta value of II by V0. So voltage shunt or shunt feedback, here the voltage shunt or shunt feedback amplifier, it provides an output voltage V0 in proportion to the input current Is. So the input current II of the basic amplifier is the algebraic sum of the source current and the feedback current. So this is actually voltage shunt feedback, which represents a trans resistance amplifier. So effect of feedback on gain, input and output impedances. So feedback is applied with the objective of improving the performance of an amplifier. So the operation of an amplifier is regulated by controlling the gain and the impedance. So the effect of feedback on input impedance for the different topologies are as follows. So here the voltage series feedback circuit which is used to calculate the input and output resistance. So here you can see Zi and Z out. Okay. So here input impedance with the feedback is given by Vs by Ii, and Vs is equal to, that is Ii Zi plus Vf. So where Vf can be given as beta V0. So using voltage divider rule, we get V0 is equal to, finally you get it as AV Ii ZL. So now substituting all these things, you have an input impedance without feedback is Vi by Ii. So current series feedback in a similar manner as for voltage series. The current series feedback we will obtain Zi with the feedback which is given by Zi into 1 plus beta Ym, where this Ym is called as a, or it is the short circuit trans admittance without feedback considering the load impedance, and it is given by the following expressions. So here Ym is a short circuit transadmittance without the feedback. So it is clear from the equation 1a, for series mixing the Z should be, that is ZIF should be greater than Zi. That is, the feedback impedance should be greater than the input impedance. Current shunt feedback circuit. So this is the diagram which shows the current shunt feedback circuit, which is used to calculate the input and output resistance. So here, to calculate these input and output resistance, so the figure which we have seen in the series previous slide, here the amplifier is replaced by its not on equivalent circuit. If AI is the short circuit current gain, then from the figure we can write the expressions for input source current and the input output current IO. So here you can see that from equation 5 and all the substitutions, we get the value of the thing to be Zi divided by 1 plus beta Ai. So the Ai represents the short circuit current gain. So similarly, voltage and feedback, you can calculate the input and output resistance. So in a similar way as we have discussed in the previous sections. So here the trans impedance come into the picture, which is denoted as Zm without feedback, considering the load, and it is given by Zm is equal to V0 by Ii. So where Zm is the open circuit trans impedance without feedback. So from equation 7b, it is clear that for shunt comparison, input impedance should be greater than the feedback impedance, which is the vice versa of the previous case. Thank you.